Terminal velocity. Concept introduction. Have you ever dropped a tiny metal ball into a honey or oil? Did you notice something interesting? Here, a tall jar with oil. A metal sphere is dropped. Its speed in the beginning is high. Later, the speed becomes constant. At first, it speeds up, but after a while, it stops accelerating and falls at a constant speed. That's called terminal velocity. When an object falls through a viscous fluid, like oil or honey, it doesn't keep speeding up forever. It reaches a constant speed after some time. This constant speed is called terminal velocity. Forces acting on a falling sphere. The sphere is falling down, so motion is in the downward direction. When a sphere falls through a viscous fluid, three forces act on it. 1. Fg, weight pulling it down. 2. Epsilon, buoyant force pushing it up. 3. F, viscous drag, which increases with speed and also acts upward. And remember, the viscous drag is in the direction opposite to the direction of motion. If your bubble goes up, then the viscous drag is in the downward direction. At first, gravity makes the ball speeds up. Then upward viscous force grows stronger. When they balance gravity, the ball stops speeding up and falls at a steady speed. That's terminal velocity. Let us take time on x-axis and velocity of the falling sphere on y-axis. When we draw a graph, we find the graph steadily increases in the beginning and becomes flat to time axis. That flat portion is called terminal velocity, Vt. This graph says it all. Speed increases at first, then becomes constant. That's final speed. You guessed it correctly. It's terminal velocity. The three forces acting on the falling sphere. The one, gravitational force responsible for weight, acts in the downward direction. The formula for it, Fg equals mg equals 4 upon 3 pi r cube rho g. The mass is replaced by volume multiplied density. The volume of the sphere is 4 upon 3 pi r cube rho g. R is the radius of the sphere, rho is the density of the metal ball, and g is the acceleration due to gravity. The second force is buoyant force responsible for upthrust. It acts in the upward direction, which is equal to the weight of the displaced liquid. So, epsilon equals the volume of the displaced liquid is 4 by 3 pi r cube and the density of the liquid is sigma, then g. The third force, viscous force, the dragging force, it acts in the upward direction because the motion is in the downward direction. The formula for viscous force is from Stokes' law, F equals 6 pi eta r Vt. Eta is the coefficient of viscosity, Vt is the terminal velocity of the metal sphere. Or radius of the sphere, rho, density of the sphere, sigma, density of the fluid, eta, coefficient of viscosity of the fluid, g, acceleration due to gravity, and Vt, the terminal velocity. At first, the sphere speeds up, As speed increases, drag force increases. Eventually, net force becomes zero. The total downward force equals the total upward force. There is only one downward force, Fg, equals the total upward force, the buoyant force, and the viscous force. Fg equals epsilon plus F. Fg minus epsilon equals F. Let us substitute the formula for each term here. We find the formula for terminal velocity. Fg is 4 upon 3 pi r cube rho g, epsilon 4 upon 3 pi r cube sigma g, F 6 pi eta r Vt. In the left hand side, we have few terms common. So 4 upon 3 pi r cube g is the common term within bracket rho minus sigma equals 6 pi eta r Vt. Here, few terms getting cancelled. The pi is getting cancelled. 1 r is getting cancelled. And this will go 2 times 2 and this will go 3 times 3. So 2 upon 3 times r square rho minus sigma g equals 3 times eta Vt. Vt equals 2 upon 9 times r square within bracket rho minus sigma times g upon eta. It's a very important formula. Vt equals 2 upon 9 multiply r square multiply rho minus sigma times g upon eta. Terminal velocity depends on. From the formula, we can write the terminal velocity Vt is directly proportional to the square of the radius of the metal sphere. A tall jar, we drop two metal spheres with different radius. The bigger one goes faster. Big raindrops fall faster than small one due to larger radius. The terminal velocity proportional to the difference in density between the metal ball and the fluid. Gas bubbles rise in water because their density is less than water density. So, the bubble rises, the metal ball falls. Because of their density difference between the object and the fluid, clouds moves upward due to similar principles. The terminal velocity inversely proportional to the coefficient of viscosity of the fluid. Here two types of fluid are here. The one with higher eta has less terminal velocity. The second fluid has higher coefficient of viscosity, so the less is the terminal velocity.